Hello everyone, welcome to the next lecture in the topic platforms for remote sensing observations. In the last lecture we discussed about geosynchronous orbits and as a special case geostationary orbits, the main purpose of why satellites are launched in geostationary orbits, and we also discussed about Lagrange points. So, if a satellite is placed in geostationary orbit, it will be observing the same point on Earth again and again. So, it will cover like a certain region of the globe, like as given in the slide, it will say this particular red circle here is kind of like an example for the coverage of geostationary satellite. It may cover like a much larger region, but for most of the useful applications will be contained within this particular zone. So, if a satellite is placed in geostationary orbit, it will not provide global coverage. It will be seeing only like a certain part of the globe, but it will provide continuous coverage over that particular part of the globe. Also, we got introduced to concept of Lagrange points, which are like special points which are which will come into effect because of the combined gravity of two objects which are in motion relative to each other, like it is kind of like a two body problem, it is moving in tandem. So, between Sun and Earth we can fix 5 Lagrange points L1 to L5, where L1, L2, L3 are like in the line joining Sun and the Earth, and L4 and L5 will be found as one of the corners or the vertex of equilateral triangle joining Sun, Earth and that particular point, Sun, Earth and L4, Sun, Earth and L5, something of that sort. So, for remote sensing application, the point L1 is used. There is a satellite called discovered with a camera called EPIC in the L1 point roughly 1.5 million kilometers away. Like here there is again a small video by NASA. I just play this. So, this is like how that particular EPIC camera sees the Earth. So, this is like when moon crossed over the Earth, the EPIC camera captured it. So, this is 3 cyclones same time in Pacific Ocean captured by this camera. The North Pole, here this North Pole, this is South Pole, this is smoke travelling, moon shadow. So, these are like another moon crossing. So, basically this is kind of like example to tell the application of observations from L1 point. Actually L1 point the satellite is placed there is for mainly for like climate applications in order to observe the Earth as a whole. So, there the time period is like it may appear like very close to the concept of geostationary orbit or geosynchronous orbit, but there are like differences, huge differences between them. So, if some satellite is placed in like L1 Lagrange point, the time period and all is not synchronized. Earth will be, this satellite will be here only, Earth is rotating around itself. So, Earth will be rotating at a different speed and the satellite will be moving along with the Sun and Earth as a whole, like Sun Earth system. The L1 point will be fixed because of the combined motion between them. So, the speed of revolution of satellite will not be synchronized with Earth and all. Earth will be rotating at a different speed, the satellite will be moving around in a different speed due to the combined effect of Sun and Earth. Okay. So, that is one thing. So, it will, if a satellite is placed in L1 point, it can observe the entire globe based on Earth's rotation. As the Earth rotates, the camera, as it is like it appears stationary with related to Earth. Okay. But at the same time, due to Earth's rotation, it will be imaging different portions of the Earth. It can see North Pole and South Pole and all, because let us say during summer what will happen, North will be, Earth is tilted at 23.5 degrees axis, right, Earth's axis is tilted. So, the camera will be here, let us say Sun is here, camera will be between Earth and the Sun. So, when Earth is tilted like this during northern hemisphere summer, the camera will be observing the North Pole. During southern hemisphere summer, Earth will be tilted like this, north will be pointing away from the Sun. So, the camera will be seeing the South Pole. So, normally if a camera is placed in L1 orbit, it can observe different parts of the globe as the speeds are non-synchronized. This is not like a synchronized orbit and all. Earth is rotating in a different speed, satellite is moving around with a different speed. Whereas a geostationary orbit, everything is synchronized, Earth speed and this thing. And also since Earth is tilted, when you see from outer space, when you move away from the Earth and observe it, we can see like the Earth's tilt, right. So similarly satellite also will be placed along the equator and it will also have the 23.5 degree tilt if you see this from outer space. Normally that will happen, okay. So these are like some small differences between L1 orbit and the geostationary orbit. Do not confuse them, they are like completely different class of orbits with completely different purposes. Lagrange points, if a satellite is placed there, it will produce extremely coarse resolution images because the distance between Earth and Sun is, as I mentioned, is 1.5 million kilometers, 15 lakh kilometers, huge distance. So the spatial resolution and all will be extremely coarse, useful for climate monitoring, climate applications, okay. But I just wanted to let you know there is a satellite from such long distances in a particular point L1 which is used for Earth observation. So the next class of orbit which we are going to see is polar or near polar orbit. So this is one of the most widely used orbit for remote sensing purposes. So what is polar or near polar orbit? I already told you, the satellite will be appearing as if it is moving from north to south like this. So this is polar orbit, Earth will be like this, satellite will be moving like this. So in geostationary or geostationary orbit, it will be moving along the equator like this. In polar orbit, it will be moving like this from north to south. That is depicted here in this particular slide. You can see like Earth is rotating underneath it, satellite is moving in its orbital plane and it will appear as if moving from north to south. So this is how basically it will rotate. Let us say the satellite is starting from here, it is kind of like start moving. So what will happen is, as the satellite completes one rotation, what will happen, it will Earth would have moved underneath it, like I draw here. See, this is Earth, let us say satellite is starting from this particular point in this orbit. So this is start moving from here, by the time it completes one rotation and comes here, Earth would have moved and now the satellite will be landing in at a new location, okay. This is starting point, by the time it comes and finishes, it may be coming at a point to the west of it. This is second orbit like this. Satellite will be moving in an orbit, Earth will be rotating underneath it. If the satellite moves exactly over pole 90 degree north and 90 degree south, we call it as polar orbit. But normally for remote sensing applications, satellite will not be placed exactly over poles, okay, not 90 degrees. It will be placed with slightly higher inclination, 98 degrees, 99 degrees and so on. The reason for it we will see later. If a satellite is placed in a near polar orbit, what will happen is the satellite orbit itself will not be fixed in space. That is, just look at this animation in the previous slide. Here you can see the orbit as if it is appearing fixed in space and Earth is moving. Normally we will think it will happen, say geostationary orbits and all are fixed orbits. It will be fixed, Earth will be moving around it, that is all. But if a satellite is placed in any angle other than like 0 degree inclination, what that is away from the equator, what will happen is the orbit will undergo precession. What exactly precession is? Similar to Earth rotating around itself, the orbit also will move around itself. Okay, so that is, you can see from this particular video, this is like highly exaggerated animation what is being shown here, but this is just to tell you like the effect of orbital precession. That is, as the Earth rotates around itself, the orbit also will be keep on rotating. See, here you can observe orbit itself will be rotating around itself. This is known as precession. The orbit also will rotate in space. Say Earth is fixed, orbit is like this, there will be kind of like an axis passing through Earth's center and the orbit center. Orbit center also will be aligned with Earth center, no issues. Earth is here, orbit is here. but what will happen is the orbit also will spin independently. Okay. If the inclination is if it lies above 0 degree. So, normally satellite will be placed with inclination greater than 90 degrees, okay, near polar orbits, 98 degrees, 99 degrees and so on. Such orbits will undergo this precession, that is the orbital plane itself will rotate. This is because of Earth's asymmetry. Earth's asymmetry is like Earth is not like a perfect sphere, it is slightly flattened at poles, bulging at the equator. Due to this thing, and if a satellite is moving in an inclined orbit, it will feel that asymmetrical nature of Earth's mass distribution, and the orbit will undergo precession, it will rotate around itself. So, this is actually, we may think it is bad, the orbit is not fixed, the orbit itself is rotating around itself in a plane. It is like kind of top you can imagine. It will have an axis, it will rotate around its axis, the orbit also will rotate. But this orbital precession is useful to us for remote sensing purposes. We will see it how. But before seeing that, just one thing I would like to tell you. If the inclination is like anything other than 0 degrees or 90 degrees, orbit will undergo precession. If an orbit is placed exactly over poles 90 degree north and 90 degrees south, the orbit will not undergo precession, orbit will remain fixed in inertial space. If you go outside of Earth, the orbit will appear as if it is fixed around the Earth, okay. It will not appear to undergo any sort of rotation. But if any other inclination is there, say 92 degrees, 93 degrees, 88 degrees, whatever, orbit will undergo precession. That is, orbit itself will revolve around itself. Okay, the orbit is precessing, and I told you it is useful in remote sensing. How? It is useful in remote sensing in order to achieve what is known as a near polar sun synchronous orbit. We already seen geosynchronous orbit, like the orbital rotation is synchronized with Earth's rotation. Similarly, for remote sensing applications, we also have orbits which are classified as sun synchronous orbits. What exactly sun synchronous orbits are, why it is needed, we will see. Let us say there is some orbit, this is the orbital plane, we are like seeing from the top, okay. So, this is the orbital plane, this is Earth, this is sun during different time period in a year. The Earth will be keep on rotating around the sun, right. If the orbit is not undergoing any precession, if it is fixed, what will happen is the angle between the sun or the line joining the sun center, Earth center and the orbit will be keep on varying. See here actually the Earth is not seen, it is like a mistake in the diagram. Earth will be like this, okay. So, this is like angles. So, this is the orbital plane, and the angle between the orbital plane and the line joining the sun and the Earth will be keep on moving. If the orbit is not undergoing any precession, say let us say the orbit is permanently fixed, Earth is rotating like this, orbit is fixed means Earth will be rotating independently, orbit will be there, nothing would have happened. If the orbit is not undergoing any precession, due to Earth's rotation around the sun, the angle between the line joining the sun, Earth and the orbital plane will be keep on varying during different times of year. This will change the illumination conditions, like what will happen is during one time sun will be overhead at a place during morning, at one time sun will be overhead at a place during evening. Solar illumination conditions will change drastically. But for in optical remote sensing we learnt that the reflectance or same object will look completely different if the illumination changes, right, which is the BRDF effect. This will be like a huge problem if the sun is continuous, if the imaging happens during different days. Let us say like I am going to acquire some images over Mumbai city. Today I am acquiring image at say 10 AM. Tomorrow I am acquiring an image at say afternoon 2 PM. After that I am acquiring an image at evening 6 PM and so on. So, what exactly will happen? I am changing the illumination conditions. As the time of observation changes, the solar illumination will change, the strength of illumination, the angle at which the sun shines, everything will change. This will severely affect our remote sensing observations. So, if we will normally try to achieve uniform illumination conditions. For that particular thing, sun synchronous orbits will help. So, in if a satellite is placed in sun synchronous orbit, then the angle between the line joining the sun and the earth and the orbital plane will always be equal, whatever be the season. So, the sun will be illuminating the earth's surface from a constant angle. There will be seasonal variation, like the amount of solar radiation coming in will vary, but at least the illumination conditions will be more or less fixed. Because the orbit is precessing, we are using that particular orbital precision to our advantage. It is a natural phenomenon. The orbital plane rotating around itself is a natural phenomenon. We are using it for our own benefit. Okay. That is one thing. And also, if a satellite is placed in sun synchronous orbit, then the satellite will be moving or observing the same spot on the earth at the same given mean local solar time or mean solar time in short. What is mean solar time? That means, let us say, if you look at like catalogs or brochures of different satellites, say Landsat, MODIS and all, they will mention what is known as a equatorial overpass time. What that signifies is, it will mention at what time the satellite will cross the equator. They will also give whether it is ascending mode or descending mode. Let us say a satellite has been mentioned 10 AM equatorial overpass time in ascending mode. What does it represent? It will say at the equator, whatever, like earth is like a huge sphere we can imagine. So, along the equator 0° axis there will be lot of places, right. Whatever be the place, like whenever the satellite crosses the equator from north to south, in ascending mode I told you, from north to south, the time will be 10 AM at that particular location at which the satellite is overhead. Let us say if the satellite is overhead in Mumbai, say Mumbai is not at 0°, but let us assume, let us say Ethiopia or somewhere closer to equator. Okay. So, the time will always be 10 AM whenever the satellite crosses that particular location. Same thing will happening even to other places. So, here what we are doing, we are making sure the sun is having like a almost constant illumination conditions and the satellite will image those locations at a constant time in order to ensure almost uniform illumination conditions and to achieve this taking images at different times of a day. So, this is known as sun synchronous orbit. Okay. So, a sun synchronous orbit is one in which the angle between the orbital plane and the line joining the earth and the sun, it will be kept constant. That is, we will make sure we will put a satellite in such an orbit, that is the orbit undergoes precession. The orbit itself will rotate and the rotation speed will be adjusted so that it will match this seasonal effect, okay, to some extent. So, this is sun synchronous orbit, and also the time of observation over a given location on the earth will be equal. This is the advantage of launching satellites in sun synchronous orbits. So, most of the remote sensing satellites are placed in near polar sun synchronous orbits. I am repeatedly telling near polar because I told you before, if a satellite is placed exactly over poles with inclination is equal to 90°, it will not undergo precession. Such orbits will never be sun synchronous. Orbit will be fixed in inertial space. If you see from the outer space, the orbit will never undergo rotation. If inclination is more than 90, typically it will be between 90 to 100 degrees, 98 degrees, 99 degrees and so on, the orbit will undergo precession and the altitude will be like matched in order to achieve this sun synchronous nature. So, as like a small example, we will calculate the rate of precession of a satellite orbit if it is in sun synchronous orbit. Okay, that is at what speed the orbit will rotate around itself. Earth is spinning, the orbit also will spin, that is like the precession. At what speed it will rotate? We will calculate its angular velocity. Okay. It is very simple to imagine, no need to derive anything, just like I will orally tell you. For a satellite in sun synchronous orbit, if an orbit has to be sun synchronous, what it has to do? It has to match the speed of Earth's revolution, that is the speed at which the orbit rotates around itself, like the precession, should match the speed of Earth's revolution around the sun, correct? That is, let us say sun is here, it is going to move in an orbit around the sun, that is orbit. The orbit also will rotate and that rotation should match this revolution speed. So, in one full year only the orbit should complete one full circle. Say the orbit is starting like this, satellite is moving like this. Slowly the satellite will be moving in like a different plane, like this it will start rotating. In one full year this orbit will complete one full circle, like 365.24 days. Okay. That will be the that will be the speed in which this orbit itself will be rotating. I am not talking about satellite speed, satellite anyway is moving in the orbit, but I am talking with the speed in which the orbit itself will rotate, the plane itself will rotate. Okay. So, in one full year the plane will complete one full cycle around itself, then that particular plane will be sun synchronous. Okay. So, typically the value will be, if you work out, we can work out the angular velocity with which such orbit rotates will be 1.991, I just write it down, the angular velocity of the orbital precession of, or I write it as precessing orbit, will be 1.991 into 10 power minus 7 radian per second, extremely small value. If an orbit rotates around itself with this angular velocity, in one full year it will complete one full circle around itself, then it will achieve the sun synchronous nature. So, if a satellite is launched in that particular orbit, it will cover one full circle around itself, and the satellite placed in such an orbit will maintain more or less uniform solar illumination conditions, and also it will overpass a given location of Earth at a same mean solar time. This is the advantage of placing a satellite in sun synchronous orbit. Most of the remote sensing satellites, Landsat, MODIS, SMAP, everything are placed in near polar sun synchronous orbits. Also there are calculations we can actually make and show that for the typical orbital height around this 700 to 800 kilometers range, normally at which we put the satellites, or like 500 to 800 I will say, the inclination angle should be between this 90 above 90 to 100 degrees. Like Landsat satellites has an inclination of around like 98-99 degrees. There is a satellite called ISAT-2 with inclination around like 91 degrees I think. So, the angle will inclination angle will always be more than 90, it will not be exactly over poles, it will be slightly away from the poles, then only it will undergo precession, then only it will be made sun synchronous. Okay. So, this is one thing, the inclination will be always above 90, less than 100, keeping in mind the altitude, the range constant. Okay. This is one thing we have to remember, and also the direction in which the satellite moves will be in retrograde, that is, let us say Earth is rotating around like this from west to east, the satellite will appear as if it is moving from east to west, it will be moving like this. Okay. Earth will be moving like this, satellite will be moving like this. So, the net effect of motion in the east west direction will be opposite to that of Earth. The satellite is moving from north to south only, but there will be like a slight component in the east west direction also, and that component will be opposite to that of Earth's motion. Earth will be moving like this, satellite will be moving like this. Okay. So, this is for satellite to be in sun synchronous orbit, the orbit will be retrograde, inclination will be greater than 0. So, as a summary, in this lecture we got introduced to polar orbit or near polar orbit. Also we started discussing about the sun synchronous orbit and why we need sun synchronous orbit. We will discuss these concepts further in the next lecture. Thank you very much.